Okay, so of course we need to talk about the assumptions of simple linear regression. And one of the key points about the assumptions is that we're going to base this on residuals. So recall that residuals are just the differences between the observed value and our predicted value. So we can write them as we would call it EI for the ith observation. It's just our actual value of y minus our predicted value of y hat. So that would be our actual miles per gallon minus our predicted miles per gallon. So assumptions, let's go through them, and we'll look at the slides in a moment. So from chapter 13, slides 24 to 29, to see a little bit more details. So the first is that we need a linear trend between the residuals and the fitted values, y hat. So the way we'll do that is we'll look at a scatter plot between the residuals and the fitted values. We'll also want equal variance of residuals, which using that same scatter plot, all that means is that the variance is equal or constant across all those values of EI. And if this assumption is violated, we say there is heteroskedasticity. So, and when we have equal variance, we call that homoskedasticity of residuals. Independent errors, so this will be satisfied if we take a random sample. We can also look at the scatter plot for independent errors. And then finally, our errors or residuals should be normally distributed. So we can do that by looking at a histogram, box plot, or QQ plot of residuals. Okay, so I like the PowerPoints for this. So here's our regression model. We're saying our residuals here are normal, centered on 0, and have sigma squared variance. And we've got linearity, independence, normality, and equal variance. So let's just go through these in a little bit more detail. So we call that the residual is the difference between the observed value and the predicted value of the response. So for each observation, 1 to n, since errors are unobserved, we look at residuals to check assumptions. So typically, we've been checking our assumptions like normality for our actual data, but in this case, we're going to just look at assumptions instead. So the first is linearity. So recall it's going to be residual on our y-axis and fitted values on our x-axis. So it's just a scatter plot. So y hat versus EI. And we're just looking for a linear trend. We don't want to see any nonlinear trend. So all that means is that, okay, you could pretty much fit a line through this, and that would be reasonable. Whereas like over here on the right, a straight line doesn't really seem appropriate. It looks like it's kind of a quadratic function or a parabola, like a U-shaped function here. So we would say that's not linear. And we don't want to see this. We don't want to see these type of scatter plots. We want to see something closer like this. The next is that they are independent. So this is more dealing with time series. So say we're recording data over time. We want to make sure there's no autocorrelation or serial correlation among the error terms. This isn't something we need to deal with in this class, but just going back to this, what you would see is over, let's say there was time on the x-axis, we would see a clear pattern over time among the residuals, and we wouldn't want that. So again, imagine if time was here, we would see, okay, well, as time goes on from 0 to about halfway, we're seeing points go decrease, and then time increases from halfway to the end, we're seeing them increase again. And that would not be okay. We would say that violates independence. There's autocorrelation among the error terms. Normality, so we would just look at our residuals and we can make a couple of different plots. So we could do, our histogram, which we're used to. We could make a box plot. We can make a normal probability plot. So we discussed all of these type of plots, chapter 6, I think, when we talked about the normal distribution. So here you would want all these points to be very close to this 45-degree line. But really, we'll just look at histograms and see, okay, does it look approximately normally distributed? And then finally, equal variance, so homoskedasticity. So these are the same plots that we were seeing before. So we would have fitted values here and our residuals on the y-axis. And what we want is this first plot, homoskedasticity, because as you can see, the variance is like from here down to here, and that stays the same across all values. Whereas like over here, we're saying, okay, there's a great big amount of variance, and then it decreases in this range, and then it increases again. Or over here, we're seeing this type, like a lot of variance at the beginning, and then as we move to the right, we're seeing that variance decrease all the way down here. So like I said, that would be the same plot as this one, just fitted values versus residual. So here we can see constant variance. The variance is about from here to here across the entire range of values. So those are our assumptions for regression. As usual, we will check them, but with small data sets, it's generally hard to check your assumptions. The important thing is we know that they exist. We know that we need them for valid analysis. So just looking at our example, so our example had like 30 observations, so it's a little difficult. So here, do we have a linear trend? Sort of. I mean, maybe a line through here. We do have this point out here, so we might think maybe it's a little bit of a parabolic shape, but this is also an outlier. So maybe I see sort of a linear relationship, a line that could go here. Constant variance, yeah, it doesn't seem super violated. Our variance is generally from like 8 to -6 throughout, and we're not seeing any correlation over time. This isn't a time series analysis. Time has nothing to do with our analysis, so we don't really have to worry about that. And then here's a histogram. So we do have it centered on this tallest bar, and then if we drew a parabola, it would look something like this. So we might say that they are not violated here. The important thing is that we just create these plots. We don't look for anything that is egregiously violated, any of our assumptions. And like I said, it's just important that we know that they exist.